going to focus here on the basic principles of petroleum seismology.
Remember that to have a commercial petroleum prospect, several requirements must be met.
There must be 1. A petroleum source rock, 2. A reservoir rock, and 3. A sill rock. Petroleum migrates from the source rock to the porous and permeable reservoir. The petroleum is trapped in the reservoir by the sill rock. So, to find oil, we have to locate the sill rock, petroleum traps, and possibly source rocks. The objective here is to describe the common way of going about locating these sill rocks, petroleum traps, and possibly source rock reservoirs. That is seismology. So, the learning objectives here are 1. A description of the seismic imaging process, from acquisitions to locations of a petroleum trap and sill rocks. 2. A description of the type of traps that the exploration and production industry is trying to image today. And 3. A description of seismic acquisition geometries, which allows us to collect data we need to image petroleum traps and sill rocks. Let's start with seismic wave propagation. Seismology is the main tool used in oil and gas exploration and production, or E&P, for imaging the petroleum traps described above. The medium for performing this imaging is called wave propagation. When the wave encounters an interface with different physical properties, that is, velocity and/or density, such as a fault or lithology change, a fraction of the generated energy is reflected toward the Earth's surface, whereas the remaining energy is transmitted to the next interface. Let us watch an example of wave propagation. Notice that reflection and transmission vary with the shape of interfaces. In other words, most shapes and characteristics of the subsurface are indirectly captured by the wave propagation. We are talking about indirect measurements here because we do not have direct access to flat interfaces and faults through the wave propagation. But flat interfaces and fault responses to wave propagation are different. These differences allow us to reconstruct these faults and flat interfaces. Sensors located in places accessible to man, such as the surface of the Earth, the water column in the sea, and boreholes in the Earth, when they are available, record this reflected and/or transmitted energy. Let me repeat this due to its importance. Sensors located in places accessible to man, such as the surface of the Earth, the water column in the sea, and boreholes in the Earth, when they are available, record this reflected and/or transmitted energy. Let us now describe the seismic imaging process. This figure shows an example of wave propagation through a subsurface model of the Earth that contains a structural trap. Due to limited space, only 3 of these snapshots of wave propagation through this model are shown here. The source used to generate waves in this example is an explosive source. We can recognize some of the reflections and transmissions at the various interfaces, especially for the snapshots corresponding to early times. For later times, pictures become very complex despite the relative simplicity of the geological model used in this example. These figures also show seismic data recorded by the horizontal and vertical arrays of sensors. Notice that the various reflections and transmissions of energy in the snapshots are also captured by seismic data. The source is then moved to another location, where the entire process of generating and recording waves is repeated. The seismic data recorded in this process are then imaged, based on arrival time and the magnitude of reflection energy to obtain the model of the subsurface. There are two important notions here: arrival times and the magnitude of reflected energy. The vertical axis indicates the arrival times and the horizontal axis indicates receiver positions. P1 and P2 show two examples of reflections with different magnitudes. The locations of reflectors are essentially based on travel times. Again, the time it takes for the wave to travel from the source to the receivers is recorded in the seismic data. From these travel times, we can reconstruct the depth of the reflector at which the recorded energy has been reflected. Let me repeat this. This is also important. Again, the time it takes for the wave to travel from the source to the receivers is recorded in the seismic data. From these travel times, we can reconstruct the depth of the reflector at which the recorded energy has been reflected. Here is a very simple description of travel times as a function of depth. We have two receivers and therefore two travel times. With two equations and two unknowns, depth of the reflector and the velocity above the reflector, we can recover the reflector depth. The magnitude of reflected energy allows us to determine what causes the reflections. In other words, the magnitude of the reflected wave allows us to determine the contrast of physical properties which has caused the reflection. Thus, we can reconstruct the locations of the various discontinuities of our geological model and the contrast of physical properties which characterize these discontinuities. Let me repeat this. The magnitude of the reflected wave allows us to determine the contrast of physical properties which has caused the reflection. Thus, we can reconstruct the locations of the various discontinuities of our geological model and the contrast of physical properties which characterize these discontinuities. This figure shows an example of such a reconstruction. Such a reconstruction can include the area above the petroleum trap, also known as the overburden, as well as the source rock. Let us now describe the type of traps that the exploration and production industry is trying to image today. What are the petroleum traps we are trying to image today? The answer is stratigraphic traps, subsalt traps, and sub-basalt traps are the three major traps we are trying to image today. We will describe this process here in more detail. There was a time when exploration consisted simply of following surface signs such as seeps, creek beds, and salt domes, and drilling where the party chief poked his stick. Those days are long gone. Petroleum seismology has revolutionized the search for hydrocarbons and has led to many remarkable discoveries. Despite these tremendous strides, most past discoveries were relatively easy compared to future exploration searches. In fact, most past discoveries have been structural traps with faults and anticlines that manifest themselves readily in seismic data, and stratigraphic traps that revealed themselves as bright spots or reflections with anomalously high amplitudes in seismic data. For years, seismic acquisition and processing techniques have been tailored to accentuate these features. Almost all of the world's such reservoirs have been found, and most have been tapped and put into production. Now, the exploration and production industry has to tackle the more elusive unconformities and pinch-outs, which have been overlooked in the past due to limitations in seismic resolution. Unfortunately, these sorts of stratigraphic traps may well constitute a significant amount of yet-to-be-discovered petroleum reservoirs. Now we will move from discussing stratigraphic traps and move into talking more about the next type of traps called the subsalt traps. Salt is one of the most effective agents in nature for trapping oil and gas. We are now finding that there are also commercial accumulations of petroleum below the salts. However, the geometry of these accumulations makes them difficult to identify in seismic data. The physical properties of salt, a density of 2.1 grams per cubic centimeter, and a velocity of 4,400 meters per second or more, are in sharp contrast to the surrounding sediments, which are generally denser and have lower velocities. The strong contrast in velocity and density at the sediment-salt interface act like an irregularly shaped lens. In the past, petroleum seismologists have treated this contrast like a mirror, producing images that portrayed salt features as bottomless diapirs extending to the deepest level of seismic data. Once seen as an impenetrable barrier to petroleum seismology probing, many salt structures are now proving to be thin blankets shielding rich reserves. Detecting these reserves requires more energy penetration than is required in traditional seismic acquisition. Let's repeat this. In the past, petroleum seismologists have treated this contrast like a mirror, producing images that portrayed salt features as bottomless diapirs extending to the deepest level of seismic data. Once seen as impenetrable barriers to petroleum seismology probing, many salt structures are now proving to be thin blankets shielding rich reserves. Detecting these reserves requires more energy penetration than is required in traditional seismic acquisition. A geological model of a small region of the Gulf of Mexico constructed by the SMART JV group, which included representatives of 4 major oil companies, describes the typical complexities of subsalt traps. Moreover, drilling through the salt is particularly difficult because the properties of salt, pseudoplastic flow under subsurface temperatures and pressures, and low permeability, make drilling through salt bodies like drilling through fluids. These difficulties increase the need for accurate imaging of the subsalt traps to reduce drilling risk. Let's now talk about the final type of traps that the exploration and production industry is trying to image these days. A significant number of hydrocarbon reserves are located below voluminous complex volcanic rock formations or sandwiched between 2 such volcanic rock formations. Most of these volcanic rock formations are basaltic, and the sedimentary layers located beneath them are broadly termed as sub-basalts. The offshore Atlantic Ocean area, for example, contains a number of hydrocarbon reserves in the sub-basalt formations. Some of these basins are currently the target of active oil and gas exploration. That is, the basins of the Faroes, West Greenland, Brazil, Angola, and the Namibia margins, as well as India and off mid-Norway. Notice that these basins stretch to very deep waters, in some cases to more than 2,000 meters. Petroleum explorationists and producers working in these areas are faced with significant data acquisition, processing, and interpretation challenges, as well as huge drilling risk due to the depth of the water column and to the presence of voluminous complex volcanic rocks located above these basins. Imaging of sub-basalt regions is generally quite complex. The complexity obviously depends on the type of volcanic eruptions, which have given rise to the basaltic rock formations above the sedimentary layers. If the eruption of the basalts was subaerial, known as flood basalts, then these basalts show a layered velocity structure. The tops of the flood basalts are commonly altered to clays with longitudinal wave, or P-wave, velocities of 2.5 to 3.5 kilometers per second, whereas the crystalline interior has velocities of 5 to 6 kilometers per second. These flood basalts typically have average P-wave velocities of 4 to 5 kilometers per second. Another major challenge associated with imaging of sub-basalt rock formations is the limited coverage of these structures by standard seismic data acquisition. This figure shows a simplified volcanic basin model. We can see that the presence of basalt in this model significantly narrows the reflection angle of sub-basalt rock formations. For a typical seismic acquisition survey, the maximum source and receiver distance, generally known as the maximum offset, is about 5 kilometers, which corresponds to less than 20 degrees of the reflection angle for sub-basalt rock formations. Unfortunately, such angular coverage is not enough to properly characterize rock formations. One needs to increase this angle to at least 60 degrees, which corresponds to a maximum offset on the order of 20 kilometers. Yet the oil and gas industry expects a more accurate definition and characterization of sub-basalt hydrocarbon reserves from seismic data in order to reduce the huge risk associated with drilling in the high temperatures and high pressures found in such deep waters. Let us talk about the actual collection of data, which allows us to determine traps of large accumulations of oil and gas. The process of acquiring seismic data is done in many ways and in several settings, or acquisition geometries. We are talking about source and receiver distributions, types of sources and receivers, types of wave generated by the sources and recorded, and more. Each setting has its own techniques, but all work on the same premise. Set off a bang, the source, let waves bounce through the subsurface, and record the reflected energy at various locations in the earth. Sound waves as a means of getting an image of the subsurface is the most powerful tool available to the exploration community. We now describe some acquisition geometries. In exploration and production of oils, we distinguish 3 cases. 1. Land or onshore. 2. Marine or offshore. 3. Transition zones, where we are not totally on land or ocean. We have a combination of the two. These examples show the continental regions, ocean, and continental margins. The concept of homogeneity, heterogeneity, acousticity, or non-viscose fluids, and elasticity controls the type of waves that we can generate and the physical quantities that we can record. Therefore, their implications for seismic acquisitions are profound. For instance, the division of seismic experiments into land and marine is primarily related to the fact that 1. In marine cases, the acquisition is conducted in water, which can be treated as acoustic and homogeneous, whereas 2. In land cases, the acquisition is conducted in heterogeneous elastic media. There are cases such as continental margins or mud, which cannot be clearly defined as marine or land. They are called transition zones. We will also discuss how seismic experiments are conducted in these cases. The concept of homogeneity, heterogeneity, acousticity or non-viscose fluids, and elasticity controls the type of waves that we can generate and the physical quantities that we can record. Therefore, their implications for seismic acquisitions are profound. For instance, the division of seismic experiments into land and marine is primarily related to the fact that 1. In marine cases, the acquisition is conducted in water, which can be treated as acoustic and homogeneous, whereas 2, in land cases, the acquisition is conducted in heterogeneous elastic media. The differences between the various acquisition scenarios come down to the difference between generating and recording waves in a homogeneous fluid and in a heterogeneous elastic medium, or solid. The fluid is generally considered homogeneous, with a relatively flat air-water interface. It supports only P waves, and both pressure variations and particle velocity can be recorded. The solid is generally considered a heterogeneous elastic medium with a non-flat air-solid interface at the Earth's surface, or a non-flat water-solid interface at the seafloor. It supports P and S waves, and the 3 components of particle velocity can be recorded. On the seafloor, pressure can be recorded in addition to the particle velocity. An explosion or any other man-made sudden deformation is used to generate waves which propagate through the subsurface. These are called towed streamer seismics, or TWS. Most acquisitions are carried in marine simply because 71% of the Earth is discovered by water. More than 85% of marine acquisition consists of a boat towing a source that fired at predetermined time intervals or distance intervals, and a set of streamers, or cables, containing the receivers, which records reflected waves. The towed streamer experiment generates and records P waves, but no S waves are directly recorded, although the wave path below the seafloor may include some S wave paths. Let me repeat this. The towed streamer experiment generates and records P waves, but no S waves are directly recorded, although the wave path below the seafloor may include some S wave paths. The S waves are not generated and not directly recorded because the receivers are in seawater, and water, like all non-viscose fluids, supports only P waves, not S waves. Let's repeat this. The S waves are not generated and not directly recorded because the receivers are in seawater, and water, like all non-viscose fluids, supports only P waves, not S waves. Yet more than 75% of all seismic acquisitions are TWS, because TWS, or towed streamer seismics, is the most efficient acquisition technique today. The second marine acquisition is called ocean bottom seismics, or OBS. In a marine ocean bottom seismic experiment, the receivers are located at the seafloor and the source are located just below the sea surface, as in towed streamer acquisition. One possible acquisition geometry is illustrated in this figure. It consists of 2 vessels, one recording vessel and one shooting vessel, which tows one or more energy sources. When the shooting is complete, the sensing system is retrieved and redeployed in a nearby location. The shooting campaign continues. In the marine ocean bottom seismic experiment, which is also known simply as a marine 4C experiment, the receivers are located at the sea floor. Every receiver station is a 4-component sensing system. That is, 3 components of the particle velocity field are recorded from a 3-component geophone, and the pressure field is recorded from a hydrophone. Again, the 3-component geophone records the ground motion at the seafloor, and hydrophone records the pressure in the water. One geophone component is oriented vertically, and 2 are oriented horizontally, perpendicular to each other. The sensing system is stationary on the seabed and is usually wired to a recording vessel. A source vessel towing a marine source array shoots on a predetermined grid on the sea surface. Only P waves are generated by the source. Now let's move to onshore seismics. On land, the commonly used source and receiver distributions are the surface seismic experiment, in which sources and receiver are at the surface of the earth. Contrary to marine experiments, in which every survey has roughly the same sources, receivers, and acquisition geometry, every survey on land is different. The example in this figure is just a particular case. The vibrisized seismic source is a vibrator, a mechanical device mounted on a truck. Several trucks may be positioned along a line to make a source array. Vibrator trucks are normally as large as garbage trucks and weigh as much as 50 tons. They have the ability to move along public roads, and sometimes they are equipped with individual wheel drive so that they can be driven almost anywhere that can take their weights. Again, contrary to marine experiments in which every survey has roughly the same sources, receivers, and acquisition geometry, every survey on land is different. Variability in types of sources, receivers, and acquisition geometries is due to accessibility. Let me repeat. Variability in types of sources, receivers, and acquisition geometries is due to accessibility. Think about the urban areas. We cannot use explosive source, for example. In jungles, we cannot easily use trucks or vibrisized source. Think about topography. That is in mountains, unconsolidated terrains, and extreme temperatures, in places such as deserts and the Arctic. Let's repeat this again. Think about urban areas. We cannot use explosive source, for example. In jungles, we cannot easily use trucks or vibrisized source. Think about topography. That is, in mountains, unconsolidated terrains, and extreme temperatures, in places such as deserts and the Arctic. The vibrisized technique is popular because the cost of operation is lower than the cost of most alternative sources, such as explosive sources, which require shot holes. A transition zone is a region where environments change rapidly, from land to the near onshore coast and vice versa. Because ships are limited by the water depth in which they can safely be used to conduct operations, and because land operations must terminate when the source approaches the water's edge, transition zone recording techniques must be employed if a continuous seismic profile is required over the land and then into the sea. As we can expect, different coastlines require different equipment. One has to be imaginative and work on a case-by-case basis. There are no standard acquisition geometries in transition zones yet. Borehole seismic experiments are generally described as a family of vertical seismic profile experiments, in which the source is at the Earth's surface, or in the water column, and the receivers are inside a borehole, or vice versa. The borehole, in the case of the VSP experiment, is generally as deep as the targeted petroleum reservoir. In summary, seismic acquisition provides us data that we can use to image the subsurface, including petroleum traps and seal rocks. The seismic imaging process is based on arrival time and the magnitude of reflection energy. There are two important notions here: arrival times and the magnitude of reflected energy. The locations of reflectors are essentially based on travel times. The magnitude of reflected energy allows us to determine what causes the reflections. Thank you for listening to this iMode Education lecture. Remember, there is a large selection of iMode Education lectures which can further enhance your knowledge of energy.